In this video, we'll see how to use 7-segment displays with the PIC microcontroller by the help of shift registers. First, we'll see the connections between the microcontroller, the shift registers, and the 7-segment displays. And then by writing C code in MPLAB X IDE, we'll create 3 examples that will demonstrate how the 7-segment displays can be driven by using just 3 pins of our PIC12F683 microcontroller. Now let's see how we are going to do the connections. This one is our microcontroller unit. This one is our shift register, and this one is our 7-segment display. We will be connecting our GP2 pin to the serial pin in the shift register. We will be connecting the GP4 pin to the shift register clock, and we will be connecting the GP5 pin to the register clock. VDD will be connected to 5 volts, VCC also 5 volts, VSS to ground, ground to common ground. Output enable will also be connected to ground, and shift register clear will be connected to 5 volts. We will be connecting the QA output of the shift register pin to the A pin of the 7-segment display, QB to the B pin of the 7-segment display, and all the connections to the 7-segment display. QH will be connected to the decimal point of the 7-segment display. So if you would like to display number 1 on the display, this means that we have to make B and C segments on, and we have to send via the shift register 0, 1, 1, and all zeros accordingly. So this will make B and C LEDs on. So we will have the 7-segment display 1 on it. So if we want to display, for example, 0 on our 7-segment display, we should make all the LEDs on excluding G. So what we need to send is all ones except G and decimal point. So this is going to display 0 on the 7-segment display. And you should also notice that this is valid for common cathode 7-segment displays, meaning that we are going to connect the COM port to ground, and we need to send 5 volts or let's say high voltage on these pins in order to make these LEDs on. If we have a common anode 7-segment display, then we should invert all these bits in order to obtain these values. And COM should be connected to 5 volts instead of the ground. Okay, let's see our connections on the breadboards. We've got our Pickit tree, and the 6 jumper cables are going through our microcontroller on this breadboard. You can see that we have our 12-volt adapter, 5-volt regulator, and going through the breadboard. And from our microcontroller, as we saw on the diagram, we have 3 jumper cables. Yellow one is for the serial, orange is for shift register clock, and green is for storage register clock. So we have 3 connections. And from the shift register, we have 8 current limiting resistors. And from those resistors, we are connecting the jumper cables. We have 8 jumper cables, and those are connected to the 7-segment display, as we saw on the diagram. So at this moment, all of the LEDs are on, and now we are going to do some modifications on it. If we see our code on MPLAB X IDE, you can see that this is similar to our shift register video. We have our configuration bits. We are defining our shift register clock pulse and storage register clock pulse functions, and these are declared at the end of our code. And then you can see a numbers array. In this array, we have 10 elements actually, and these are corresponding to the numbers that we are going to display on the 7-segment display. First one is 0, second one is 1, 2, 3, 4, and this is ending at 9. So make sure that you are using a common cathode display because you can see that we have connected the common pin of the 7-segment display to the ground, since this is a common cathode display. So we are going to have a high voltage on these pins in order to display numbers on the LEDs. If we had a common anode display, then we would be connecting the common pin on the device to 5 volts, and then we would send 0 or low voltage in order to make that segment on. So that's why these numbers are corresponding to a common cathode display. And we are defining this int data to send. We are setting our pins as output. These are the pins for our microcontroller. And then we are setting them as 0 in the beginning. Then I'm creating a loop which is going to start from 0 and end at 9. And it's going to assign the numbers array to the data to send variable. So we are going to be seeing the numbers on the 7-segment display. And as you can recall from our previous video, we have our send bit function, which is sending a 1 or a 0 according to the number that we are going to send. And then we are sending a shift register clock pulse, and then we send the storage register clock pulse, so that we will be able to see the finished number. And then we create a delay of 1 second, and that's it. So let's save this code and build it. And load it on the microcontroller. Okay, it's connecting to the programmer, configuration memory, and it's complete. So as you can see, it started counting from 0. It's going to end at 9 again and starting from 0. So you can play with the code as you wish. You can count the numbers from 9 to 0. You can do other things. You can display other characters that you can display on the 7-segment display. In our second setup, we are going to be using a 4-digit 7-segment display, HS5461B. This one is common anode, and don't get confused with this A that I have in the picture. This is going to be B. So again, let's start with our connections from the microcontroller to the shift register. We have our GP2 pin connected to the serial pin of the shift register. So I will show it this way. GP4 will be connected to shift register clock, and GP5 will be connected to register clock. VDD will be connected to 5 volts, VCC to 5 volts, and shift register clear to 5 volts, VSS to ground, ground to common ground, and output enable to ground as well. If we take a look at the 7-segment display's pinout, we can see that we have the A, B, C, D, E, F, G, and decimal point connections. And these are identified by these numbers, starting from 11, 7, 4, 2, 1, 10, 5, and 3. And we've got 4 more pins. Pin number 12 makes the first digit on. Pin number 9 makes the second digit on. And pin number 8, the third digit. And pin number 6, fourth digit. So this means that if we send high voltage to pin 12, it's going to display a number, or let's say a character, whatever it is, according to the values it has in these pins. For example, if we would like to display 1 on the first digit, let me highlight it like this, we need to set the B and C segments on. So let's try to organize these 12 pins like this. So I will have 12 values, and let's assume that I'm connecting the 12th pin on the first digit, 9th pin on the second digit, 8th pin on the third digit, and 6th pin on the 4th digit. And for the rest, I will follow these sequence. 11, 7, 4, 2, 1, 10, 5, and 3. So I would like to display 1 on the first 7 segment. So I need to make it on. So I will send 1 bit to pin 12. And the other 3 pins are going to be zeros. And since I want the B and C segments to be on, which are connected to 7 and 4, since this is a common anode display, I need to send zeros on those pins. So I need to send 0 here and 0 here. The rest needs to be 1. Okay, this means that if this sequence is sent to the pins of the 7th segment display, the first digit is going to display 1. So this means that with these 4 digits, we are selecting which display is going to be on, and in the rest, we are defining which number or which symbol is going to be shown. But we have a problem here, then that is from the shift register we can get only 8 outputs. And that's why we need to find a solution, and that solution is going to be cascading shift register. So we are going to add another shift register to our setup. Okay, now we have our first shift register here, and we have our second shift register here. First connection that we are going to do is we are going to connect the P9 of the shift register 1 to the serial input of the shift register 2, and the storage register clock will be connected to the storage register clock of the shift register 2, so they will be the same, and the shift register clock of the first shift register is going to be connected to the shift register clock of the second shift register, so they will be synchronized. We will again have 5 volts on VCC, and ground will be connected to the common ground, and output enable will be connected to the ground, and shift register clear will be connected to 5 volts. Actually, with this setup, these 2 shift registers are going to work like a single shift register which has a single serial input and 16 outputs. So when we send a series of bits like this from our microcontroller, it's going to be shifted towards the first shift register first, and then it will continue being shifted to the second shift register. So if I start to send this data from the microcontroller towards this setup, but sending the most significant bit first, the output is going to be QD will be 1, QC will be 0, QB will be 0, and QA will be 0. So this is this part of our data. And in our first shift register, we are going to have 1, 0, 0, 1, which is this part, and we will have 1, 1, 1, and 1 in these sections. From this picture, you can easily see which pins should be connected to which pins on the 7 segment display. So we have 12 to be connected to QD, 9 to be connected to QC, 8 to be connected to QB, and etc. So the picture is going to get messy, but you can easily match which pin is going to be connected to which pin on the 7 segment display. Okay, you can see that we have made our second setup here. We have added our second shift register, and we have synchronized it with the first register with the shift register clock and the register clock pulses, and we are using its first 4 bits as we showed in the diagram, and over 330 ohm resistors, they are going through the 4-digit 7 segment display. So we have 12 jumper cables going to our 7 segment display. Now let's check our code. I have added this numbers_CA for common anode These numbers are starting from 0, ending at 9. However, you can see that I have added 4 extra digits in the beginning because I'm going to make an OR operation with the digit array. I'll tell you how it's going to work. And this digit integer array is going to correspond to which digits we are going to send the numbers to. So in the main loop, we are defining our pins as output. We are defining some integers. And here you can see that we have 2 loops nested inside. And you can see that we are doing this OR operation with the numbers and the digit. So each time we do this operation, we are going to make an OR operation with an element of the digit and with an element of the numbers underscore CA. And then after this operation, we are going to start sending the bits starting from the most significant bit. You can see that the iteration is starting from 11 and it's going to end at 0. So we are going to get the most significant bit first, and then the next one, and so on, as we saw in our previous diagram. So this code is already running on the microcontroller right now. You can see that it's counting from 0 to 9 and it's repeating itself, and first displaying on this digit and continuing to the left. Now let's try to make some changes. For example, let's change the direction of the digits. We should change the index to 3 and then decreasing to 0. Okay. In the previous example, we had shifted a single number through the 4 digits. In this last example, we'll see how to display 4-digit numbers on the display. Let's check our new code. Here you can see that in the while one loop, we write down the 4-digit number that we would like to see on the display. And in order to send it digit by digit, first we define a 4-element integer array, ARR, and assign the digits of our number to it. To get the first digit, which is a multiplier of 10 to the power of 3 or 1000, we divide the number by 1000. Please pay attention that since we defined the array as integer, we will only get the integer part of the division result. In this example, we are going to divide by 1000, and the result is going to be 2 since we defined it as an integer. In the next line, we divide the 4-digit number to 100 and then use the modulus operator with 10. This will give us the remainder, and if we perform the calculation for our example, it's going to be 2156 divided by 100. We will get 21, and if we use the modulus operator with 10, we will end up with 1 as the remainder. In the next line, we divide the 4-digit number to 10 and then use the modulus operator with 10 and get the remainder. So we are going to have 2156 divided by 10, and our result is going to be 215. And then using the modulus operator by 10, we are going to get 5 as the remainder, which will be our 3rd digit. And in the next line, we use the modulus operator by 10, so it's going to be 2156, and the remainder will be 6. So we will have 2, 1, 5, and 6, which is the number that we would like to send. In the for loop that we see here, we send the 12-bit data to shift registers one by one. The code is already running on the microcontroller now, and you can see the numbers being shifted with a slight delay. But our purpose was to display the 4-digit number 2156. How shall we manage that? We can send the digits one by one. This is a constraint of our 7-segment display. Here we'll be taking advantage of the capacity limits of the human eye. As we decrease the delay between the shift of the digits to a certain level, we will stop seeing this shift and we will start to see a constant 4-digit number. Let's experience this with reducing the delay from 200 milliseconds to 20 milliseconds in our code. Let's save and build it. Let's try to build it again. There might be some problems. Okay, build is successful. And load it to the microcontroller. And you can see that we still have a shift. We can still see it, but it's so fast. I mean, we can see whole numbers. So maybe it's better this way. If I just show it to you like this. So we see 2156, but we still see a shift or flicker. And let's, for example, reduce it down to 5 milliseconds. And save and build and then load the code. And we can observe the whole number here. And you can see it. But we still some kind of a wave effect. This cannot be observed with the naked eye. I cannot see it, but when I look at the camera that I'm recording with, I still see this wave effect that is on the 7-segment display. So what I'm going to do is I'm going to delete whole delay from the code, save it, build and run it. Okay, now we see a constant 4-digit value here, 2156. Actually, even though we deleted the whole delay, we should still be aware that we have a delay due to the instructions that we are running on our microcontroller. However, since we are running at 4 MHz operating frequency and the instructions in the loop can take about just a few processor cycles, we are talking about delays at the levels of microseconds. For this human eye constraint, you can check this flicker fusion threshold article on the web. In this video, we saw how to cascade shift register and use them in order to drive a 4-digit 7-segment display. Shift registers are really useful devices when it comes to expand the pins of the microcontrollers. They allowed us to drive a 12-pin display with using just 3 pins of our tiny microcontroller. You can change the code in order to display several numbers with a loop, or you can even display some variables that are updated in your microcontroller, such as the ADC conversions, which will be our next topic for this tiny microcontroller. This was the end of the video. I hope it's been useful for you. If you have any questions or comments, please write them in the comment section. Thank you for watching and see you in another video.